In our last video, we looked at the following example and finding the derivative of this function. And I want to look at this problem again, but from a slightly different point of view. So one thing we could have done at the beginning last time was rewrite this thing. So this is the product of two different functions inside of a logarithm. And one thing you might remember from a college algebra class is that logarithms have some nice rules for simplifying and rewriting. So one of them says that we can take products inside a logarithm and rewrite them as a sum. So I'm just going to do that here. So what this says is that this will be the ln of x squared plus the ln of the square root of 3x to the fourth plus 1. Now from here, again, we can simplify even further because another nice logarithm rule that we have is that if we have log base a of some m raised to the r power, that with logarithms that m, that exponent, can come down in front. So we can rewrite this as r times log a of m. So we can go ahead and rewrite these things. So this square root here, we've been doing this. This is really to the 1/2. So we can rewrite this as 2 times the ln of x plus 1/2 times the ln of 3x to the fourth plus 1. And now we've got some nice sort of basic logarithm functions that we can differentiate. So now if we go ahead and take the derivative of this thing, y prime, so 2 is going to stay the same because that's just a constant, and then 2 times the derivative of the ln of x, so that's 2 over x. And then for the other one, we'll have 1/2 times 1 over 3x to the fourth plus 1 times the derivative of this inside here. So derivative of 3x to the fourth is just going to be 12x cubed. And here we are done with our derivative. If we compare that to what we had previously, we had this. And notice that within this, we didn't even simplify the function at all. And so this is a bit of a mess, and this logarithmic differentiation makes it a little bit cleaner. We just had to do a little bit of algebra work up front. And we can take this idea and use it to differentiate other functions. So as an example of something we haven't seen before, so if I take the function x to the x, so we have the function really isn't defined at all points because taking negative fractional exponents of negatives can be dicey, but we do see that we get what we expect for the rest of this. So let's go ahead and figure out the derivative of this function. And our technique is called logarithmic differentiation, and what it is using properties of logarithms along with what we've learned about implicit differentiation to help make our task easier. So how I'm going to start is I'm going to take the natural logarithm of both sides of this equation and rewrite this. So I would have ln of y, and then I'm able to bring this x down front here and just have x times ln of x. So now I can take the derivative with respect to both sides. So on the left, we get 1 over y times y prime. This is really what I'm doing here is when using this f of x equals y sort of notation that we've done in the past. So when we take the derivative of ln of f of x here, we get 1 over f of x times f prime of x. I'm just doing that same thing. I'm just using y here instead. And then on the right, we have a product rule. So the derivative of x is just 1. So we have 1 times the ln of x. And then we leave the x alone and take the derivative of the natural logarithm. We get this. And so what we get is y prime over y equals ln of x plus 1 over x, which is really just 1 here. So we have ln of x plus 1. So from here, what we want to do, we still haven't solved for it because we always want to figure out what y prime is. So what I'd have to do is multiply both sides by y. So I'd have y times the ln of x plus 1. And from there, we want to make this substitution back in for y. So y was originally x to the x. So our derivative here is x to the x times the natural logarithm of x plus 1. And so if we wanted a concrete example for this function at the point 1, 1, if we plug in 1 for this, we'd have 1 to the 1 ln of 1 plus 1. So this is really just 1. So what we'd expect is that our tangent line here would be y minus 1 time equals 1 times x minus 1. And let's go ahead and check that. And there we see we do have a tangent line that we would sort of expect to have there based on our picture and based on our work for the derivative. So for one more example in this video, let's find f prime of x for f of x equals 3x squared plus 2x, that whole quantity raised to the 6th power, divided by sine squared of x times 6x cubed plus 2x plus 1. Now, we could go ahead and do this using techniques that we have learned in previous sections. We could use the product and the quotient and the chain rule all together at once. And let's just I'm going to add a 7th power in front of my term in the denominator there. And we could do that and it'd just be really sort of a mess. And so logarithmic differentiation can help us clean this up a little bit. So let's rewrite this as ln of f of x, and we'll take the natural logarithm of both sides. Now, the one logarithm rule I have not reminded us of is one for division inside of logarithms. So that rule, and we'll probably need a little more space anyway, is when you have the log base a of m divided by n, that this is log base a of m minus log base a of n. So we can split division up as subtraction here. So let's go ahead and do that. So what we'll get is the natural logarithm of 3x squared plus 2x all raised to the 6th minus, we'll take the logarithm of the bottom here, so sine squared of x times 6x cubed plus 2x plus 1, and that whole quantity raised to the 7th. Now, we can keep cleaning this up a little bit. So for one thing, this 6 out in our exponent can come down in front. And then this whole second bit here can be split up using our first rule for splitting up logarithms. Log base a of m times n is equal to log base a of m plus log base a of n. And so let's go ahead and do that. And so we get 6 times the natural log of 3x squared plus 2x. And then we'll have minus, and we'll have ln. And I'm going to be careful with this minus here. So we'll have sine of x. And I'm just going to rewrite it so it's sine of x squared, the way we sort of expect it to be. And then this will be plus the ln of 6x cubed plus 2x plus 1, all raised to the 7th. Now, we can do a couple more things, just this setup sort of problem before we've even taken the derivative yet. We're just doing a whole bunch of setup to make our life easier. I want to distribute this negative, and I want to take these exponents that I have down in front of my logarithm. So what we'll have is 6 times the natural log of 3x squared plus 2x minus 2 times the natural log of sine of x minus 7 times the natural log of 6x cubed plus 2x plus 1. And now finally, I feel like I am ready to take the derivative of both sides of this thing. All right, so when we take the derivative on the left, we get 1 over f of x times f prime of x. And on the right, we will get 6 times 1 over 3x squared plus 2x times that derivative of what's on the inside there. So that will be times 6x plus 2. And then we'll have minus 2 times 1 over sine of x times the derivative of the inside, which is cosine of x. And then minus 7 times, is 1 over 6x cubed plus 2x plus 1. And then we take that derivative of the inside here and get 18x squared plus 2. And we can clean this up just a little bit, and we'll need to multiply over by f of x here. So we'll have f of prime of x equals f of x, and then let's make this 36 plus 36x plus 12 over 3x squared plus 2x minus, this will be 2 times the cotangent of x, and then we'll have minus 126x squared minus 14 plus 14 there, and then all over 6x cubed plus 2x plus 1. And then to finish this thing off, we need to put f of x back in. So we would start back up with that original function that we had up here for f of x. So we get this expression here times this 36x plus 12 over 3x squared plus 2x minus 2 cotangent of x minus 126x squared plus 14 over 6x cubed plus 2x plus 1. And while this doesn't seem necessarily like a big improvement, it was actually much easier to compute these than it would have to go ahead and use the chain, product, and quotient rules, because to do the derivative of the top, we'd need the chain and power rule. To do the derivative of the bottom, we would need the product rule and the chain rule, and it would just get to be a bit of a mess, and this actually simplifies the entire process.